I wanted to finish up a little bit, one more thing about the ON model before we go to the more general problem. So we had set up this Lagrangian where we wrote the phi field. Okay, I should write bigger phi field as V plus rho, some rotation transformation times n0, and we had worked out what the Lagrangian was. And one other thing I wanted to mention is that the ON model has a bunch of symmetry currents coming from the ON symmetry, and they're the standard form phi transpose in this case, phi transpose TA d mu phi minus d mu phi transposed TA phi, where the TA are all the ON generators. So that's the standard form for a scalar current when there's a symmetry. Oh, thank you. Okay. And so if I plug this into here, I get V plus rho squared times n0 transpose C transpose TA d mu C n0 minus the other minus n0 transpose d mu C transposed TA Cn0. So you just plug this in, and it turns out that all the terms where the derivative acts on the rho cancel out. So the only terms which survive are the ones which have a d mu C here. And we wrote last time that C was this exponential of some matrix. And so if I plug that into here and go to the EFT, so that is to say I set this to V squared. So that's, sorry, the first step would be to go to the EFT Lagrangian where we have dropped the rho field. So the current just becomes the same formula, but this V plus rho squared is just V squared. And then what I do is I take this C, which has some exponential of xa pi a, and start expanding. And since this piece is a derivative of C, when I start doing the expansion, 1 plus I xa pi a plus dot dot dot, this term starts off as order pi. It's linear in pi, and then you'll get pi squared, pi cubed, etc. terms. And so to order pi, which means just set this to 1 and keep the derivative from here, what it turns out is that the current is, I got minus 2V d mu pi a, and then plus higher order terms. So the interesting thing is normally in field theory or something, when you're doing these currents for scalars, they're quadratic in the fields. But now when you go to the Goldstone boson, this current is a term which is linear in the field. And you know that the charge, the conserved charge, is the integral d3x of j0a. So the conserved charge is linear in the pion, and what that means is that when you act with the charge, which is like an infinitesimal symmetry transformation, you produce a Goldstone boson, and that's our old idea that if I'm here and my Goldstone bosons are little fluctuations of the scalar field about my reference point, but that's exactly what a charge transformation does, a broken symmetry generator. It moves the field a little bit. So this formula is for sorry, I should mention this, for a broken generator, not too many A's, but a broken generator. If A is an unbroken generator, then this linear term won't be there, and this thing will start quadratically in pions. And in particular, the matrix element between the vacuum and J mu A for a broken index, and pi in this case is 2IV, this pion of momentum P. So a current has a non-trivial matrix element, a non-zero matrix element to produce a Goldstone boson from the vacuum or annihilate a Goldstone boson from the vacuum, this coefficient is proportional to the strength of the symmetry breaking. And this is basically a generic feature of spontaneously broken theories with Goldstone bosons. Okay, so we're going to repeat all of this for QCD, and you will see that all of these features go through, and the analog of V will be F pi, the pion decay constant. Okay, so I set up the ON model, and now I just want to go back to CCWZ, but in a more abstract sense, because for the ON model, we had a picture of a sphere with some scalar field, and things could move, but now we have some general theory. It may be, the symmetry may be broken non-perturbatively. We have no idea what's going on. So I want to repeat this construction for a generic G mod H sigma model. Yeah. No, because I mean, here we have a perturbative theory, so the pions are the.
So I can just think of like it as an analytic.
Yeah, because the Lagrangian was, you know, the Lagrangian started off, we wrote this pi fields, and the Lagrangian started off as d nu pi a, d nu pi a. So it's all, so now you quantize this and so on. So it's whatever the mode is corresponding to the state. Yeah. Okay, so so we saw that basically the Goldstone boson was related to this transformation, which takes my reference vacuum to the local vacuum that I have, that is starting from phi 0 and going to some point where there's a phi. So the field which is introduced already in the ON model, you can see C of x was this field I was introducing. If I just set this to V and forget about the rho, then this is the dynamical field which is entering in the Lagrangian. So I'm going to switch notation a little bit. So what, for reasons which will become clear later, I'm going to call it capital C. So C of x is my field. It's parametrizing the local vacuum. It's the transformation I need to get from my standard vacuum to the broken vacuum. And the CCWZ prescription is you just write it as the exponential of the broken generators times the pion fields. And I'll use different things for pions here. So in this notation, the pion is dimensionless. In QCD, we'll put an F pi down here to make it have dimension 1, but it doesn't really matter. It's the coefficient in front of the exponential of the broken generators. And CCWZ call this little c, but in chiral perturbation theory, there's something else called little c. So I'm just calling it capital C, and you can follow their papers. So schematically, there's some reference vacuum, and I have some point here. Let's say I make this transformation like C, and that gives me the, that's the field configuration. Okay, C of x is telling you where I am on the space of vacuum states of the theory. Now I can apply a G transformation to it because the original theory had a symmetry group G. So this C goes to something which is C over here. Now this is not a matrix in the standard form. That is, it's not the exponential of the broken generators. So you can write the same field as some directly as the exponential of the broken generator. So this is some C prime of x. But when you get here, any transformation which gets to this point can differ by some h, some unbroken rotation on the, so in other words, we discussed this last time, there can be an h factor here, an element of the unbroken group. So if you think of rotations in 3 dimensions where you can see all of this, these exponentials, the c's would be like e to the I jx pi x plus jy pi y. I now multiply by an arbitrary group rotation, so that's some e to the I jx theta x plus, there's not space here, but theta y plus jz theta z. And the product of these two rotation matrices, so rotating this way followed by rotating that way, is not the same as some rotation by e to the I jx pi prime x. So this would be like my standard rotation going along the lines of longitude and coming up to this point, but it can differ by that by some jz rotation over here. So this is theta h or something. Okay. Because you have to end up at the same point, so the two matrices have to be in the same coset, but they can differ by some right multiplication by h. And that's because you want to put it in this standard form of an exponential of only the broken generator times pi. There's no unbroken generator contributions in the exponent. Okay, is this clear? Yeah. Like this, because we're working in a neighborhood of the origin. So, I mean, this is the Baker-Campbell-Hausdorff formula that e to the a, e to the b is e to the a plus b plus a half a commutator b plus, I forget, it's something like. So you can always write it this way. Because geometrically, this is some point in the group which corresponds to a particular element of the coset. And this is another group element which corresponds to the same coset. And they have to, they can differ by some right multiplication by the h. So if I act on the vacuum state, G C omega is C prime H omega, and that's the same thing as C prime omega. So you can, the H gets factored out. Right, I mean, if you just think of this here on the sphere, to get to this point, I can make an arbitrary rotation about the z-axis followed by this great circle rotation through here. So if I go this way with 2 steps, and I end up at this point, I don't know whether that's the same as this great circle rotation or it could have an extra z rotation involved. Well, because it's just counting the number of parameters because this is an arbitrary group. So even in the case of rotations, right, you can write a rotation as e to the I jx theta x plus jy theta y plus jz theta z. But you can also write it in terms of Euler angles as e to the I alpha. Or let me do a different thing. Alpha I alpha x jx e to the I alpha y jy. You can also write it this way. You have 3 independent rotations and you can get everything from it. And near the origin where the transformation is small, it's essentially just take power series and solve order by order. Okay, but the important thing to remember here, C of x is some Goldstone field and the field can fluctuate. So this point can move around as you move around in space. So it can depend on x. G is global, so it does not depend on x. But the h on the right-hand side can depend on x because you're solving this point by point, and because c depends on x, the net h that you get can depend on x. So even though you're making a global transformation, this h that you have can be x dependent. And h, in fact, is not arbitrary. It's a function of the original c of x and g in some calculable way, which depends on the structure constants in the group and I mean, you can't write it down in closed form, but you could do it as a series expansion, for example. So the transformation law that they have, C of x goes to C of x, H inverse of x. So that's that transformation law, where both C and C prime, well, this is C prime, is a purely an exponential of broken generators. Now what we did in the ON model was we basically took C of x times n0, and that transforms to C H inverse of x n0, but now this is just n0 because H was the thing which left the reference vector unchanged, so that's why we were able to, well, this thing is just what I call little c n0 over there. So that's what we did in the case of the ON model. But this is the generic form for any symmetry group. We're not really assuming we have a scalar field or some perturbative thing or whatever. We're just saying the vacuum is characterized by a group element. And not really specifying anything about what the vacuum is. I don't know, is this clear? No? Okay. Okay, so now we go to QCD. So the Lagrangian is a sum over flavors of Q bar I, the covariant derivative QR minus the sum on R mass terms minus the gluon field strength tensor and then possibly a theta term. Maybe it's 16 pi squared. I don't know, somehow the different, when you write on the iPad, suddenly sometimes things get deleted if you touch them. Okay, who knows? I'll have to check this coefficient, whether it's 16 pi squared or, and it's 32 pi squared. So that's a possible topological term. Now the quarks we have, so U, D, and S are traditionally called light quarks in the sense that their masses are small, well, small compared to, let's say, 1 GeV. And C, B, and T are called heavy quarks for the reason that their masses are large compared to 1 GeV. And for the heavy quarks, for mesons and so on, we use heavy quark effective theory, which Matthias talked about. And the chiral perturbation theory is going to be used for the light quarks. And then you can argue whether the C quark is heavy enough to use HQET and whether the S quark is light enough to use chiral perturbation theory. But for many things, the C does behave like a heavy quark and the S does behave like a light quark. So let me look at the QCD Lagrangian for just the light quarks. And we're going to treat the mass as small, that is the mass as a perturbation. So we're going to first set the masses to 0 and then include the mass as a correction term and do perturbation theory in the mass. Just like HQET is a perturbation theory in 1 over m, here for the light quarks, we have a perturbation in m. So I'm going to define Q to be U ds, and I'll have Q left and Q right, which are just the left-handed U left, D left, S left, or U right, D right, S right. So the kinetic term here, the Lagrangian, can be written as Q bar, this D slash, by the way, is the QCD D slash. So it's Q bar I D slash Q which is the same thing as q bar ID slash q left plus q bar right ID slash q right. The mass term, so the kinetic term, the lefts and rights are independent, not coupled to each other, because this term and the first term involves only the left-handed quarks, and the second term only involves the right-handed quarks. And the mass term, q bar q, will be q bar left, q right, plus q bar right, q left. And this is the term which couples left to right, but we are dropping the mass term, so we don't have anything like this, and we have the lefts and rights independent of each other. So this theory has a global, well, it has more than this, but it has a global SU3 left cross SU3 right symmetry, under which Q left goes to L, Q left, Q right goes to R, Q right, and L and R are 3 by 3 unitary matrices with determinant +1. So you're mixing up UD and S by some 3 by 3 unitary transformation, but you're making independent transformations on the left-handed UDS, that's the L, and you're making, and on the right-handed ones, which is R. And clearly this Lagrangian has that symmetry, because if this is a global transformation, then on here you would get an L here and an L dagger, and here you would get an R and an R dagger, and they just cancel because they're constants and they can be brought through the D slash. Now, we also have two U1 symmetries. So I've broken this up into SU3 and the U1 part of the unitary group. So Q left can go into, I'm going to do it this way, into Q left, and Q right can go into e to the alpha Q right. So this is what's called the vector U1, where both the left and the right-handed transform the same way under the phase rotation, and this is the this is baryon number, because all quarks are transformed the same way by the phase rotation. And we have, what is the sign? Doesn't really matter. Q left goes to e to the I alpha Q left, and Q right goes to e to the minus I alpha Q right. So this is what's called the axial U1, under which left and right-handed quarks transform oppositely to each other. Now for U1, which is an abelian group, you can take the left-handed, you could have a left-handed U1 in which this is alpha left, and a right-handed U1 where this is alpha right, and I can take linear combinations to make the vector and the axial vector. For the SU3 cross SU3, you cannot write an SU3 vector is well defined, but SU3 axial does not exist. It is not a group. So this would corresponding to generators TA left plus TA right. And this would correspond to generators like TA left minus TA right. But if you commute two generators of the form TA left minus TA right, you get a vector generator. So this is not a group, and you shouldn't think about it that way. And so, but for the U1, because everything, all the commutators are 0, you can make this transformation. And think of, instead of left and right, vector and axial. Okay, questions on this? Yeah. Yes. That's correct. You can have an H. That's why. Yeah, if you had everything in here, then you wouldn't. But then you have you have redundant variables you don't want, because you want a unique parameterization of the vacuum, at least locally in some region. Yeah. Okay. So now the reason for doing this is that there's a famous, the axial anomaly, which says that d mu, the divergence of the axial vector current, the singlet axial vector current, is the number of flavors times g squared over 32 pi squared g mu nu duo. So this is the famous anomaly. It tells you that the U1 axial current, the thing corresponding to this transformation, because lefts and rights being opposite to each other is the same as the gamma 5. The gamma 5 has a +1 for right-handed quarks and -1 for left-handed, and I'm summing on all the flavors of quarks, so that's why it's the U1, is not a symmetry. So the original theory had, if you want 18 generators, 9 in the SU3, sorry, 8 in this SU3 left, 8 in the SU3 right, and then one U1 vector and one U1 axial. But this U1 axial is actually not a symmetry. So the original theory has an SU3 left plus SU3 right cross a U1 vector symmetry. Okay. So that's my original theory. And so we discussed this in the question session yesterday. So the claim is, or the assumption is, that this symmetry is spontaneously broken by some condensate, whatever, some non-perturbative thing, down to the SU3 vector symmetry. Remember, SU3 vector is a group spontaneously, okay? And some non-perturbative dynamics takes place, and I'll just assume this. So this is the pattern of symmetry breaking, and the U1 just goes along for the ride, U1 vector. So really, the breaking is taking part in the non-abelian sector. And so G mod H is SU3 left plus SU3 right over SU3 vector. And this is a particularly simple form of coset because this is isomorphic to the group SU3. But generically, if you broke SU3 to SU2 and looked at an SU3 cross SU2 coset or something, that's not a group. But in this particular case, it looks like the group. So we have 8 broken generators, which are the Goldstone bosons. And they are the pions, so pi plus, pi minus, pi 0, the k plus, k 0, the k 0 bar, k minus, and the eta. So I've written this way. This is an isospin triplet. There are 2 isospin doublets and an isospin singlet. And just one thing I wanted to point out is that the phase conventions, well, okay, I'll come back to that when I write down the particles. So if you had the U1 axial being broken, there would be a 9th Goldstone boson, the so-called eta prime. And there was a famous puzzle, which was, why is the eta prime so heavy? Why isn't it look like a Goldstone boson? And it 't Hooft figured out, so this was Weinberg. He had a paper called the U1 problem. This was the U1 problem. Why isn't there a 9th Goldstone boson? He was able to prove that there should be a Goldstone boson whose mass was, I think it was square root of 3 m pi or something, and there isn't one. And basically, the same year, 't Hooft figured out the anomaly and showed that there is not a Goldstone boson because this is not a symmetry. So if you don't have a symmetry, then Goldstone's theorem doesn't apply, and you don't need a Goldstone boson. Okay. So any questions on this? Yeah. Yeah. No, because the axial part is broken. So neither U1L nor, okay. So if I do Q left goes to e to the I alpha left Q left, and Q right goes to e to the I alpha right Q right, then the analogous thing would be some divergence like this, which would be proportional to alpha left minus alpha right. So there would be the symmetry current. So the divergence of the left-handed current, well, you can see from the gamma 5. So the divergence of the right-handed current would be a half of this, and the divergence of the left-handed current would be minus a half of this. And so when you add the two together to get the vector current, they add up to 0, but if you subtract them to get the axial current, you get that. So neither of these is a symmetry. It's only the combination, which is U1 vector, which is a symmetry. The non-abelian part, so this is coming from a triangle diagram where you insert a current and put gluons here. The non-abelian part has a TA, this flavor generator TA, and when you do the loop, you get a trace of TA, which is 0. And so the non-singlet currents, the pieces which are in SU3, have no anomaly because the trace of the generator is 0. So only the trace piece, which is the U1 part, has an anomaly. Okay. So now we can go back to the CCWZ formulation for QCD now. And so what is my, so here, so I need a group element G. And the group element G, I will write as L comma R, because my group is SU3 cross SU3, so it has some SU3 left transformation and some SU3 right transformation. H, which is in the unbroken subgroup, has to be a vector transformation, and it's not the best notation, but I'm just going to write it as H comma H instead of introducing another symbol. So both the left and the right-handed transformations have to be equal. Because it's a vector transformation, I'm just calling them both H. So the generators of G are, if you want TA left tensor 1 and 1 tensor TA right, that is, the TA lefts are in the left-handed space and the TA rights are in the right-handed space. The H generators, which are the vector generators, are TA left tensor 1 plus 1 tensor TA right. That is, I'm making the same transformation on the left-handed part and on the right-handed part. So this is like here. And then for the broken generators, the XAs, I have to pick something which when combined with the H generators gives me the whole linear space given by all the generators. And the standard convention here is to pick the axial, even though the broken generators don't form a group, so we can take TA1 minus 1 tensor TA, right? Because if you combine these two sets, you get everything up here. Okay. And the normalization I'm going to use is that the trace of TATB is a half. So that's the standard normalization that people use for SUN theories for the generators. Okay, so any questions on this? Okay, so now let's look at what Xi is. So Xi is the exponential of the broken generator. And here's the broken generator. So when I exponentiate it, let me define a little, so this is where little Xi comes in, is e to the I Ta pi a, and I'm going to put the f phi back in here because now for QCD we will use the pion decay constant. So this just makes that pion there, which was dimensionless, back into a variable of dimension 1. When I exponentiate this, You can see in the left-handed space, I get T tensor 1. So I just get C. But in the right-handed space, there's a minus sign here. So I get e to the minus I Ta pi af in the right-handed space. In other words, the right-handed transformation is C dagger when I take the exponential of this generator, just because of the explicit minus sign in the broken generator. And the pi a's here, which are the 3 by 3 traceless matrix, is 1 over root 2, and then here I get pi 0 over root 2 plus 8 over root 6, pi minus, k minus, pi plus. So these are the standard labels, k0 bar, yeah, k plus, k0 minus 2, 8 over root 6. So this is the matrix. If you're doing SU3 chiral perturbation theory of the mesons, normalized to trace TATB is a half, and then you can see that's true for all the neutral particles, and then the pi plus, etc., defined as like pi 1 plus I pi 2 over root 2, and so on. Yes, you're right, pi AT. The thing, yeah, the thing up here, in the X, that's right. And just a warning, because I've wasted time on this. If you write the matrix this way, which is the way everybody writes it, and you use the standard, what's called the standard Condon-Shortley phase convention for isospin or spin, that is the standard angular momentum relations with raising and lowering operators, then the actual SU2 multiplets are pi minus, pi 0, and minus pi plus, k0 and k plus, and then here it's k minus and minus k0 bar, and the eta. Okay, so if you use Clebsch-Gordon coefficients to try and relate pi plus and pi minus and pi 0, you got to be careful that there's a minus sign here when you write things in terms of this matrix versus using Clebsch-Gordon coefficients. So this would be the m equals minus 1 state, m equals 0 state, but it's minus pi plus, which is the m equals 1 state, etc. Yeah. So when you're doing the group SU3, you just have a TA, and TAL and TAR are some TA, but acting only on the left-handed quarks and only on the right-handed quarks. So here, when we're doing this transformation, this I can write as e to the I TA, and then let's call the parameters epsilon LA or something. So if you write an L, or you could write this as TL, but the matrix as a matrix is the same. The L just means whether it acts on the QL or whether it acts on the Q right. There's some 3 by 3 matrix which acts here. So which ones? No, these are the SU3 generators. So neither the broken are the combination of these two. Here, it's this combination. The generators where the same TA acts on the left and the right is not broken, and the one where the thing acting on the left is the opposite of the one acting on the right, that's the broken generator. So in other words, the transformation, well, it is exactly this transformation. You're making some transformation, Q left goes to some UQ left, and Q right would go to U dagger Q right. That's the thing which is broken. But this is a 3 by 3 matrix, and that's what these T's are, the 3 by 3 matrix. And the unbroken one is Q left goes to UQ left, and Q right goes to the same UQ right. This is unbroken. And that's broken. So what I'm now doing is writing the U, basically, which is the T. So that's this 3 by 3 matrix. And that's why the transformation on the right-handed part is the dagger of the one on the left-handed part. Because it's the broken transformation. And the H would be both are the same. So there's an SU3 group, but there are two of them. So this TA is the SU3 transformation, and then the left and right tells you whether it acts on the left-handed quarks or the right-handed quarks. Okay. So now what is the transform? Okay, I was about to erase this, but this is the transformation I want. So I have C prime is C prime dagger is G. So G is L comma R. C is C dagger. And H inverse, because I'm putting this on the other side, is H inverse comma H inverse. Oh, yeah, this formula. Okay. And so everything is now, there are two groups, so everything is two factors. So and this is why I call the CCW thing capital C, so that now I can use little c in here. Okay, so this is the same as our equation over there, just written for SU3 cross SU3. Is this clear? There are two blocks. There's one 3 by 3 block for the left and a 3 by 3 block for the right. So in fact, in those Schladmig lecture notes, I wrote it in some block form, but this is just to save space. Yeah, that's right. But now you can see that what you're getting is C prime is L C H inverse or H dagger, and C prime dagger is R C dagger H dagger. You get a double, you get two relations. And if I take the Hermitian conjugate or the inverse of the second relation, this gives me C is H C R dagger. And the first one, I'll just write it again. So here's the transformation rule. So I'm given some C. Okay, I'm given C, and I'm given L, and I'm given R. So that's the original C, the capital C, which is this and the dagger, and then I'm given the G transformation. I multiply it this way, and I have to solve both of these equations to determine what H is. H is to be consistent between these two equations, and this will determine H as a function of L, R, and the original C, and so H is a function of X. So this is this weird, what looks, if you haven't seen it before, is a weird transformation law. So this field C transforms this way. You can use either form, and depending on where you're using it, one version may be more, may simplify the result compared to the other one, but they're equal. Now, if I take something which I call capital sigma, which I define as C squared, okay, that's the definition, then sigma transforms to, sorry, what am I doing here? This is C prime. Transforms to C prime squared, but I can use, for one of the C primes, I can use the first formula, and for the second C prime, I can use the second formula. So this transforms into L C H dagger times H C R dagger, and now you can see the H dagger cancels, so the sigma goes to L sigma R dagger. So there are two kinds of fields which are used in chiral perturbation theory. One is little c, which is e to the I pi over f, and capital sigma, which is e to the 2I pi over f. One's the square of the other, and sigma has a nicer, well, it transforms in a much nicer way. And if you're just doing mesons, it's perfectly fine to work with sigma, but when you start doing matter fields like baryons and so on, the Xi is more useful. And actually, I mean, even in the meson literature now, people use this other form. And there's some papers by Banans, Colangelo, Ecker, which go through this formalism. And if I have time, I will go discuss their formalism in a little more detail. The difference between what they're doing and what I'm doing, they define a little u, which is 1 to e to the I pi a t a over f. They define a capital U, which is e to the I 2I pi a t a over f. And basically everything looks the same, except that their u transforms like u goes to r u L dagger, and their little u, u prime, is r u h dagger, which is h u L dagger. And I don't know, it got me very annoyed that the right-handed transformation's on the left and the left-handed transformation's on the right. But other than that, everything's the same. So basically, if you apply parity to this, the mapping between the two is their U is Xi dagger, and their big U is sigma dagger. But they're writing things still as exponentials of I pi, and so their pion, so let's write it this way, their pion is the negative. There's a minus sign in the pion. So you can translate from one to the other. But I was going to switch to this notation, but then I noticed that their R is on the left, and I'd prefer to keep the left-handed transformation on the left, but it doesn't really matter. I'll come back to this if I have time. That's another way to think about it. There's a way to do it that as a different choice of the broken generator. But I'll do it this way because in people are, there's some advantages to introducing the little Xi and so on. Yeah. I think if you take the broken generator probably as just T left or something and not the T right, then you just get the sigma directly. Again, this is in that Schladming notes. I think there's a section where I discuss another version, but let's just stick with this for now. Okay, so we have our basic field. Our basic field is either, well, let's just think of it as little Xi, because sigma is the square of that. And now what do? We write down the standard procedure. So write down the G invariant Lagrangian. So G invariant means SU3 left cross SU3 right invariant Lagrangian made up of Xi. The most general possible thing. Everything you can write down, which is Lorentz invariant. And then, well, and has to satisfy this transformation law, either the Xi transformation law, or if you use sigmas, it has to be invariant under this sigma transformation. So that's step one. Step two, just as for any of the field theories or the EFTs I mentioned, you have what are called integration by parts identities. Which is basically d mu of something. The integral of that is 0, so you can basically you can integrate by parts. Two operators which might look different. If you can get one from the other by integration by parts, you don't include both of them. The third is field redefinitions. And then the fourth, which I'll discuss, is in the case of chiral perturbation theory, there's something which is called a Cayley-Hamilton identities, which I'll discuss, which is just which will come in when we discuss SU2 versus SU3 chiral perturbation theory. And we will see that the power counting for chiral perturbation theory is essentially that the power counting parameter is that derivatives, it's a counting in, so you count powers of momentum. A derivative counts like p to the 1 because a derivative is a factor of momentum. The sigma matrix or the U matrix is order 1, p to the 0. And we'll see that well, let's get to the quark mass matrix when we include perturbation, when we include this. So I'm going to first start with no external sources, no mass terms, just pure Goldstone bosons. So I have this Xi, and actually it's easier in this case if I don't have baryons to use, where's it gone, the sigma field instead. And then people work out what they would call NF arbitrary chiral perturbation theory, which would be generalizing that matrix to an NF by NF matrix, maybe a 4 flavors, 6 flavors, whatever, or NF equals 3, which is SU3 chiral perturbation theory, or NF equals 2, which is SU2 chiral perturbation theory. So for SU3 chiral perturbation theory, that's the matrix I wrote. SU2 chiral perturbation theory, you just keep the pions. So you basically kill this part of the matrix. You just keep this piece and drop the eta. And that's the matrix for SU2 chiral perturbation theory. So the other notation I'm going to use is I'm going to use angle brackets to denote a trace. Okay, so let's start with no derivatives. So 0 derivatives. So I have a sigma, which transforms like L sigma R dagger. And I want to write down terms which are invariant under this transformation law and have no derivatives, so they can only depend on sigmas. Okay, so what can I write down which is invariant? Okay, you got to cancel all the L's and R's when you do the transformation, otherwise the term would be invariant. So you could take sigma dagger, sigma, which would transform like R, so you have to take a trace of this, and the trace of that will transform to the trace of R sigma dagger, sigma R dagger. But since it's inside the trace, you can pull the R to the other side, and then this is sigma dagger sigma. So it's invariant. But what is sigma dagger sigma? Okay, sigma is the exponential of some SU3 generator, so it's a unitary matrix. So sigma dagger sigma is 1. So you're getting the trace of 1, which is NF, or for the arbitrary flavor case. So you can try writing down, try anything you want, but basically it should be obvious that you'll never get anything which depends on fields, because you'll have basically multiple traces of sigma, sigma daggers. Then you could do sigma dagger, sigma, sigma dagger, sigma. But again, this is a trace of 1, etc. So So this tells you that our Goldstone bosons, again, are derivatively coupled. There is no term with zero derivatives. So the first term is two derivatives. And so that's called the p-squared Lagrangian. That's f squared over 4, the trace of d mu sigma dagger, or d mu sigma dagger, d mu sigma, either way. I guess with what I said, I would put angle brackets for the trace. Now here, just like in the case of sigma dagger sigma, the L's and R's cancel because L and R are constant matrices, so the derivative doesn't do anything to them, so they all cancel over here. But now d mu sigma dagger is no longer 1. So that's the unique term, in fact, at this order. If you tried something like the trace of d mu sigma dagger times the trace, you maybe square of this or something, you can verify that this trace is 0. It's proportional to the generators. Maybe I'll mention this again, but you can check that this is 0. So this other possible term isn't there. There's a single term at this order. And to work it out, let me just say that I'll write sigma as e to the x. X is just to avoid complicated things. So sigma is 1 plus x squared over 2 plus dot, dot, dot. And then d mu sigma is d mu x plus a half d mu x plus x d mu x plus dot, dot, dot. So you should all check this calculation. Now you just plug into here, and if you work it out, you will find that the Lagrangian starts off as the trace of d mu pi. So the reason for putting the f squared over 4 here is that when you expand to the x's to second order, you get f squared in the denominator and the 2's, anyway, so you end up with this, the f's cancel. And then the next term, the first non-trivial term, is the trace of pi commutator d mu pi squared. And then you get 6 pions, 8 pions, etc. So just like in the ON model, we get an infinite series of terms. The 4 pion, 6 pion, 8 pion interactions are all related to each other with no parameters other than f pi. Because I normalized my generator to TA, TB is a half, this is the same thing as 1/2 d mu pi a, which is the correctly normalized kinetic term for scalar fields. And that's what fixes this coefficient to be f squared over 4. It's picked to be f squared over 4 so that this thing becomes 1/2. But this is the first non-trivial interaction. And you know that this is the commutator of two generators, so this can be, this term can be written as minus 1 over 6 f squared times the structure constant FABC, the structure constant FAGH, IB d mu pi c, pi g d mu pi h, because the commutator of pi with d mu pi gives me a structure constant, and then similarly for the second term. And maybe the best for SU2, where the structure constants are epsilon ABC and epsilon AGH, and then epsilon's contracted gives me like delta BG, delta CH, minus the other combination. This is 1 over 6. So for SU2, this is 1 over 6 f squared pi dot d pi squared minus pi dot pi d pi, which is similar to what you saw in the ON model, some structure like this. So the first interaction is governed completely by F pi, and it has this form for SU2 perturbation theory or some slightly more complicated form for SU3. And then the next term will still have 2 derivatives and 6 pions and so on. And in general, if you expanded this whole thing out, you would get something I could write as 1/2 d mu pi a d mu pi b times what's called the metric GAB of pi, where this is basically the metric tensor on this curved G mod H space, which in this case is a group. So this is the metric tensor for the group. And what is this function? You just have to read it off. So the first term here is delta AB. And then from here, you pick out the coefficient of d mu pi. So this term, for example, would give me 1 minus, I guess 1 plus 1 over 6f squared. This term would give me pi dot pi. This is delta AB. This is minus pi dot pi delta AB. And this first term would give me pi A, pi B. And then you can keep going. Okay, so if you do a series expansion, you would get a series expansion of the metric. So this is the nonlinear sigma model. It has some non-trivial couplings, but everything is 2 derivatives. I think it's time, right? Yeah. So let's stop here, and then I'll discuss the higher order terms after the break. Questions? Okay. I'm not going to explicitly do like these expansions, but basically you just take e to the I. I mean, it's literally this. You just have to keep the order correct when you take the derivatives and then do the traces. So it's a slightly painful algebra, but